Neyman-Pearson's lemma. Neyman-Pearson developed this lemma in 1933, and it is considered as the foundation of the testing of hypothesis. Basically, that is the foundation of the theoretical testing of hypothesis. To find the best test procedure, this lemma helps to find the test that has the highest power. So, how we define the highest power? That the power of the test is the probability of rejecting the null hypothesis when it is really a false. So, in this module, we just understand the statement of the Neyman-Pearson's lemma, and then we see different application of this lemma. So, the statement of this lemma is: let x1, x2 up to xn, where n is the fixed positive number, denote the random sample from the distribution having the probability density function, that is f of x theta. Then the giant distribution of x1, x2 up to xn is generally represented as the likelihood function, that is L of theta x1 up to xn, and that is equal to f of x1 theta, f of x2 theta, and up to so on f of xn theta. Let theta dash and theta double dash be the distinct values of the parameter space. As we have just did in the previous module, we are assuming two different values from the parameter space, that is theta dash and theta double dash. Similarly, we also take the two distinct values from the parametric space, and we can write it as gamma, which is representing the overall parameter space, and that is based on theta, and we are assuming the two possible values in that parameter space, that is theta dash and theta double dash. And let k be the positive number. Define C as the subset of the sample space such that the following conditions must be fulfilled. The first condition is that the likelihood under the null hypothesis, which is denoted by theta dash, for all the values of x, and the alternate likelihood of the alternative hypothesis, that is theta double dash, then the ratio of these two must be less than or equal to the k, which is assumed to be a positive number, for x1, x2 up to xn for C. And for the second, that is the ratio, again we are assuming a ratio, that is the alternative case of this one, the ratio of the two likelihoods under the null hypothesis and under the alternative hypothesis, that is greater than k for x1, x2 up to xn, and that belong to the C steric, that is the complement of the C. And the last one, that is the most important, that the probability of C under the null hypothesis, that is alpha. Then C is the best critical region for size alpha for testing the simple hypothesis against the alternative hypothesis, that is theta is equal to theta double dash.